Linked Lists, Part 1, Introduction. You have already seen how data is organized and processed sequentially using an array called a sequential list. You have performed several operations on sequential lists, such as sorting, inserting, deleting, and searching. You also found that if data is not sorted, the searching for an item in the list can be very time consuming, especially with large lists. Once the data is sorted, you can use a binary search and improve the search algorithm. However, in this case, insertion and deletion become time consuming, especially when large lists are involved, because these operations require data movement. Also, because the array size must be fixed during execution, new items can be added only if there is room. Thus, there are limitations when you organize data in an array. A linked list is a collection of components called nodes. Every node, except for the last node, contains the address of the next node. Thus, every node in a linked list has two components: one to store the relevant information, which is the data, and one to store the address, which is called the link. And this is basically the address of the next node in the list. The address of the first node in the list is stored in a separate location called the head or first. The list in this figure, 16-2, is an example of a linked list. The arrow in each node indicates that the address of the node to which it is pointing is stored in that node. The down arrow in the last node indicates that this linked field is null pointer. For a better understanding of this notation, suppose that the first node is at memory location 1200 and the second node is at memory location 1575. We have this figure 16-3 that actually depicting this setting. The value of the head is 1200. The data part of the first node is 45, and the link component of the first node contains 1575. The address of the second node is actually 1575. If no confusion arises, then we will use the arrow notation whenever we draw the figure of the linked list. Because each node of a linked list has two components, we need to declare each node as a class or a struct. The data type of each node depends on the specific application, that is, what kind of data is being processed. However, the link component of each node is a pointer. The data type of this pointer variable is the node type itself. For the previous linked list, the definition of the node is as follows. Suppose that the data type is integer. Struct node type, and then you have an integer which is holding info, and a node type which is a link and is a pointer. When you want to declare a variable of this linked list, you simply do node type and you name the pointer, which in this case we named the pointer head. To help you better understand the concept of a linked list and a node, some important properties of a linked list are depicted here. Consider the linked list in figure 16-4. This linked list has four nodes. The address of the first node is stored in the pointer head. As you can see, it is 2000. Each node has two components: info to store the information and link to store the address of the next node. For simplicity, we assume that info is of type integer. Suppose that the first node is at location 2000, the second node is at location 2800, the third node is at location 1500, and the fourth node is at location 3600. Therefore, the value of head is 2000. The value of component length of the first node is 2800. The value of the component length of the second node is 1500, and so on. Also, the down arrow in the component link of the last node indicates that this value is null pointer. The number at the top of each node is the address of the node. Now look at the table. This table shows the values of head and some other nodes in the list shown in the figure. A quick review tells us the head value is 2000. The head info, basically the information that his head is pointing to, is going to be 17. And the head link, which basically is the component link of this member, is 2800. And of course, the head link info, which is the information that this specific link is pointing to, is going to be 92. And so on. So you can have the exact same setting for every single of these nodes. Note that we are using the pointer member assignment notations over here. Suppose that current is the pointer of the same type as the pointer head. Then the statement current equals head copies the value of head into the current. Look at the figure 16.5 on this slide. Clearly, in this figure, you can see the current value is 2000, the current info is 17, the current link is 2800, and the current link info is 92, as we had it in the previous slide. Now consider the statement current equals current link. This statement copies the value of current link, which is 2800, into the current. Therefore, after this statement executes, current points to the second node in the list. Remember, when working with the linked list, we typically use these type of statements to advance a pointer to the next node in the list. In figure 16-6 that you're looking at right now, the current is 2800, the current info is 92, the current link is 1500, and the current link info is 63. Finally, if you note that movement happens, we can say head link is 1500, head link info is 6300, and then head link info is 45. Try not to get confused here, as it is simply moving the pointer current from one element to the next element. From now on, when working with linked list, we will use only the arrow notation. Now let's talk about traversing a linked list. The basic operations of a linked list are as follows. Search the list to determine whether a particular item is in the list, insert an item in the list, and delete an item from the list. These operations require the list to be traversed. That is, given a pointer to the first node of the list, we must step through the nodes of the list. Suppose that the pointer head points to the first node in the list, and the link of the last node is null pointer. We cannot use the pointer head to traverse the list, because if we use head to traverse the list, we would lose the nodes of the first list. This problem occurs because the links are in only one direction. The pointer head contains the address of the first node contains the address of the second, and the second node contains the address of the third, and so on. If we move head to the second node, the first node is going to be lost, unless we save the pointer into a specific place. If we keep the advancing head to the next node, we will lose all of the nodes of the list from the beginning as soon as we do the advance. Therefore, we always want head to point to the first node. It now follows that we must traverse the list using another pointer of the same type. Suppose that current is the pointer of the same type as head. This code on the slide actually traverses the list. So we set the current to head because we want to start from the beginning. Then we go through a loop, a while loop, and while current is not equal to null pointer, which basically checks if we have arrived at the end of the list, we do our processes, and each time we do the processes, then we set the current to the link that current is linking to. Basically, we are setting the current to go and look at the next item in the linked list. For example, suppose that head points to a linked list of numbers. The code you see on the slide actually outputs the data stored in each node. So what we do is we set the current to head again, and then through a loop while we are not at the end, which is checked by current is not equal to null pointer, we see out the current info, look at the notation. As I said, from now on, we're going to use this notation, the arrow notation, for accessing the elements and the pointers and working with the lists. So here we set we see out the current info, and we put a space at the end of it, and then we simply set the current to the link that this current item is pointing to, which means we're moving to the next item. Okay, now let's talk about insertion. Consider the linked list shown in the figure 16.7 on this slide. Suppose that P points to the node with info 65, and the new node with info 50 is to be created and inserted after P. Consider the following statements. We create a new node over here, then we set the information of the new node to 50, which is our target, and then we set the link of this new node into the link of P. So basically we let the link to point to 65. Remember, we are inserting over here, right? So whatever item comes in here, it should link to the next item, and that's what happens over here. Okay? And then the link of the P is going to be set to the new node. So basically the new item is going to be inserted here, pushing all the items down, and P is going to be pointing to the new item. Note that the sequence of statements to insert the node is very important, because insert new node in a list, we usually only use one pointer P. And this is the only thing that we use to adjust the links of the node of the linked list. Using two pointers, we can simplify the insertion code somewhat. Suppose Q points to the node with info 34. The order in which we run the new statements and execute them do not matter in this case. To illustrate this, suppose that we execute the statements in any order, either plink equals new node or new node link equals Q or vice versa. As you can see in this table, table 16-2, the effect of using these at the end of the day is going to be adding the new node. It doesn't matter which one comes first. So either the new node arrow link equals Q comes first, or the plink equals new node comes first. The result always is going to be the same. Now that we talked about insertion, it's time to talk about deletion. Consider the linked list shown in the figure 16-10. Suppose that the node with info 34 is to be deleted from the list. The following statement removes the node from the list. So basically, you do P arrow link equals P arrow link link. So simply assigning the link to the next item to the current link, and you can get rid of an item. Figure 1611 shows the resulting list after preceding statement executes. From figure 1611, it is clear that the node with info 34 is removed from the list. However, the memory is still occupied by this node, and this memory is inaccessible. That is, this node is dangling. To deallocate the memory, we need a pointer to this node. So let's see how we're going to get rid of this dangling information. So here's the code. You do set q to the link of p, and then the link of p is going to be set to the link of q, and at this point we can delete q. Table 16.3 shows the effect of this statement we actually executed. So at the first step, you set the q to the link that p has, so right over there. Then you set the link of the p to the link that q has, so basically you jump it over here. Instead of pointing forward, it's going to jump over there. And at this point, you just go back and delete whatever is in p. Let's quickly review. So at the beginning, we have p that is pointing to the 65, right? So the link of p, which is this yellow one, is pointing to 34. So what we do is we're going to set the q to the link of p so that q is also pointing to 34. So that's the first step. Let the q point to 34. At the next step, as you can see, whatever q link was pointing towards is going to set to the new link of p. So basically now p is going to point where the link of q was pointing to prior to this step. Okay, so that means we basically are connecting 65 to 76, which means that link 34 is not in the sequence anymore and basically is going to be out. So then we run delete q, which means delete whatever q is pointing to, which is 34 at this point, and 34 is going to be out of the game. And this concludes Introduction to the Linked List Part 1. In Part 2, I will be showing you how to build a linked list.